Lesson 8.3 is on adding and subtracting radical expressions. This goes back to when we were first simplifying algebraic expressions. The idea stands for when we add and subtract radical expressions. We can only add and subtract like radicals. Two or more radical expressions are like radicals if they both have the same index and the same radicand. So for example, if we have 9 square root of 7 and 4 square root of 7, these are like radicals because they both have the same index of 2, which remember is indicated by this radical here. So even though we don't write the little 2 in front of it, that means we're taking the square root, so it has that index of 2, and it has the same radicand of 7. So we would actually be able to combine these, or add or subtract them if it asks us to do either one. If we added the 2, they would be 13 square root of 7. If they asked us to subtract those 2, we would have 5 square root of 7. And we can do that because, again, these are like radicals with the same index and the same radicand. The next two are examples of what are not like radicals. So for example, we have the cube root of 5 and the cube root of 6. So even though they have the same index, they have different radicands and are therefore not like radicals. Then for this last example, we have the square root of 2 and then the cube root of 2. And again, these are not like radicals. So even though they have the same radicand, they do have a different index on each of them. One is a 2 and the other one is a 3. So these are not like radicals. So for our examples, we're going to be adding or subtracting if possible. Assume that all variables represent non-negative values and be sure to simplify your answer. So for this first one, we can see that our radical expressions have the same like radicals. They both have the cube root and the radicand is 4y. So we can go ahead and combine these. And basically what we're going to be doing is we're going to be subtracting the two numbers out front. So we got 2 minus 7, which is going to be negative 5. And then we just keep this cube root of 4y on the end. For number 4, we have this cube root of 3x plus 3 times the square root of x minus 9 times the square root of 3x. So not every single one of these are like radicals. So the only two that are like radicals are this one expression out front and this expression in the back here. So we could rewrite this. I'm going to rewrite the 3 square root of x out front and then have my plus square root of 3x and then minus 9 and then square root of 3x. So these two here are what we're going to be able to combine. And keep in mind that in front of the square root of 3x there is a 1 there. We just don't write it. And so now we're going to do 1 minus 9, which is negative 8. So our final answer for this one would be 3 square root of x and then minus 8 and then square root of 3x. Or you could write it as negative 8 square root of 3x plus 3 square root of x. So you could flip-flop these, just make sure that the subtraction sign stays with this 8 because it is indicating that this part here is negative. For number 6, we have two terms inside this radical expression that actually are alike. So we have 11 square root of 5 and this minus 8 square root of 5 because they have the same radical. And then we have a negative 5 square root of x and this 4 square root of x. So if we rewrite this so that the like radicals are next to each other, we would have 11 square root of 5 minus 8 times the square root of 5. And then I'm going to rewrite this as plus negative 5 square root of x, just so that way we don't lose track of that negative there. And then plus 4 square root of x. So I just rewrote this problem so that our like terms were next to each other. So now taking a look at this one, we're going to be able to actually do the 11 minus the 8. And so we'll have 11 minus 8 is 3, so we'd have 3 square root of 5. And then negative 5 plus 4 would be a negative 1. So we would have negative 1 times the square root of x, or just negative or minus the square root of x. And that would be the final answer for this problem. For number 8, we have the square root of x divided by 4 plus 3/8 times the square root of x. So I'm going to rewrite this so that this 1/4, because this is a fraction here, it's just wrote as this division sign right now, I'm going to rewrite that out front of our square root of x. So that way we can see hopefully a little bit more clearly that we have the same radical of the square root of x. And so now we can just basically do our operations with fractions. because we're going to be able to combine these. So 1/4 is the same as 2/8. So we have 2/8 times the square root of x plus 3/8 times the square root of x, and this equals 5/8 times the square root of x. And that's it for that problem. For number 10, as we're looking through this, even though they all have the cube root of 2, there's actually only 2 of these terms that we'll be able to combine, because now we have to make sure we're paying attention to all the different variables that are going on outside of the radical. So the 4xy and the 3xy are going to be combined to make 7xy, and then we'll have the cube root of 2, and then minus 5x, and then the cube root of 2. So we can leave our answer like that, or they have sometimes wrote this as we basically factor out the cube root of 2, and then we'd be left with 7xy minus 5x, and then we'd have the cube root of 2 on the outside. So you could go even further with it and write it like that, or you can just leave your answer, which is what I'm going to box. You can leave it just like this here. So, or you could factor it and get that answer there. Now for number 12, we don't have any variables involved, but this is now one where we have to do some simplifying of this radical in order to see if there is anything that we can do to basically subtract these two radicals. So the square root of 63, we can break this down into the square root of 9 times the square root of 7. And then the 28 we can write as the square root of 4 times the square root of 7. So now that we have these perfect squares, we can actually take the square root of those. So we're going to have 3 times the square root of 7 minus 2 times the square root of 7. And then after doing that subtraction there, not that they have the same like radical, 3 minus 2 is 1. And so we're left with just the square root of 7. On number 14, we're going to do the same idea as the last one. So we're going to rewrite this. We're going to have 3, and then instead of writing it as square root of 48, we're going to write this as the square root of 16 times the square root of 3, since 16 times 3 is 48. And we're writing it that way again because we want to factor out any of those perfect squares and actually evaluate that. And then 24 we can write as the square root of 4 times the square root of 6, so we can break it apart into that. And then we can do this right here and actually get 3 times 4 times the square root of 3, because the square root of 16 is 4. Square root of 4 is 2. And then we can simplify this. We'll have 12 times the square root of 3, and then minus 2 times the square root of 6. And this is actually as far as we can go with it. Even if we tried to break that 6 down into where it says the square root of 2 times the square root of 3, it's really not helping us to further simplify this problem. So this is as far as we can go with our answer, and that is all that you need to do for that one. Number 16, we have these two fractions underneath the radical signs. So we have the square root of 3/16 plus the square root of 27/4. And so this we're going to use our the quotient rule that we had talked about in the previous lesson, where we're going to break this down so that it says the square root of 3 over the square root of 16 plus we have the square root of 27 over the square root of 4. The top here, the square root of 3, we're just going to have to leave as the square root of 3. The square root of 16 is 4, 4, so we can write that there. And then the square root of 27, we're going to break that down into the square root of 9 times the square root of 3, because again, we're trying to break it down into a perfect square if it can be factored into that. And then the square root of 4 is 2. So now going further with this, I'm going to go ahead and rewrite this as a fraction, because at some point I'm going to end up having to add fractions. So we're going to write this as 1/4 times the square root of 3. Plus, then we're going to have 3, so square root of 9 is 3. So this is going to be 3/2 times the square root of 3. So when we add fractions, we need to make sure that we have a common denominator. So this here, we're going to have the 1/4 square root of 3. 3/2, we're going to rewrite it as 6/4 square root of 3. And now adding these, we would have 7/4 and then square root of 3. For this next example, we have the square root of 180 minus the square root of 150 minus the square root of 45. So again, we're going to try to break these apart into their factors where hopefully one of them is a perfect square that we can actually take the square root of. So the square root of 180, we can break this down into the square root of 36 times the square root of 5 minus, then we have 150, which we're going to break apart into the square root of 25 times the square root of 6 minus, and then the square root of 45, we're going to rewrite that as the square root of 9 times the square root of 5. And so now that we have a perfect square for each of these, we can actually evaluate that. The square root of 36 is 6, so we'd have 6 times the square root of 5 minus 5 times the square root of 6 minus 3 times the square root of 5. And then going through and combining our like radicals, we would be able to do this subtraction here, the 6 minus 5, or sorry, 6 minus 5, the 6 times the square root of 5 minus 3 times the square root of 5. And then that's going to give me 3 times the square root of 5 minus 5 times the square root of 6.